Hi everyone! In this video we are going to use what we learned about nucleophiles and we'll apply that to an SN1 example. Now often what we can do in a substitution reaction is choose a solvent that is the same as the nucleophile, and that makes things a lot easier. Now, this isn't always the case, but often enough we can use this method. So let's look at an example where the nucleophile is the same as the solvent. All right, so this is our electrophile, or our substrate. And then our nucleophile is methanol. But methanol is also a good solvent, so we can kill two birds with one stone. Okay, so if this is an SN1 reaction, what would happen first? Would the leaving group leave, or would the nucleophile attack? The leaving group will leave first. So remember, in SN1 reactions, it's a first order reaction, and that tells us that only one of the reactants is going to do something. So in this case, the leaving group will leave first. So looking at our electrophile, what is our leaving group? Iodine. And how do we know that iodine is our leaving group? So let's compare leaving groups. If iodine leaves, it takes it takes electrons with it. So it ends up as a negatively charged ion. But what if CH3 left? It would take electrons with it as well, and it would have a negative charge. So which would prefer to have the negative charge, the iodine or the methyl group? Iodine. Remember, carbon tends to really want to be neutral. It can be negatively charged or positively charged, but it does not accommodate a negative charge as easily as iodine. Iodine's also really large, so iodine can accommodate that charge really easily. So that's how we figure out the leaving group, and we'll talk more about leaving groups in the next lecture as well. Okay, so iodine will leave, and we'll end up with our intermediate, which is a carbocation. And I'm drawing the methyl group as a planar bond here just because once that fourth bond leaves, the carbon that is positively charged is no longer a tetrahedral carbon. It's now a trigonal planar carbon, technically. Now, what type of carbocation do we have? Is this primary, secondary, or tertiary? Tertiary. And remember, SN1 reactions prefer to have something stable like a tertiary carbocation or a secondary carbocation. So that's partly why this is an SN1 reaction. All right, so we also have I- hanging out. And it usually kind of hangs out around the carbocation initially. So it almost kind of partially blocks the nucleophile from attacking. Remember, that's from our stereochemistry discussion. Now you might also remember that the nucleophile can attack from above or below. So if the nucleophile attacks from above, would we end up with a retention product or an inversion product? Retention, because the iodide was above the molecule, and if the nucleophile also attacks from above, then we're going to retain any possible stereochemistry. Now, what if the nucleophile attacks from below? Well, the only other option is the inversion product. All right, so let's draw those two products. So let's draw the retention product first. So the methanol will bond, oops, I drew that wrong. So the methanol will be a wedge because it's attacking from above. And the methyl group will be below in a dash. Now, are there any formal charges on this molecule? Yes, so remember, if oxygen is bonded to 3 different groups, it tends to be positively charged. It does have a lone pair on there as well. And let's also talk about the inversion product. So if methanol attacks from below, what would we end up with here? So the methyl group would be above the plane in a wedge, and the methanol will be below. But additionally, that oxygen has a positive charge too. Okay, so let's look at these two products. What is the relationship between these two products? Are they constitutional isomers, enantiomers, diastereomers, or are they identical? So if you're not sure where to start, are there any stereocenters? No, there are no stereocenters. So you might be tempted to say that the carbon bonded to the methanol is a stereocenter. However, if we try to, let's say, rank these two carbons next to it on the ring, they're equivalent, so we have to go down the chain. But those two carbons are also equivalent, and then we just end up at the same spot. So really, there's only 3 groups bonded to that carbon. Now, if we had, let's say, a methyl group over here, then that would be different and we would have a stereocenter, but we don't have any other substituents on the ring, so those 2 groups are equivalent, so that is not a stereocenter. Okay, so that kind of rules out enantiomers and diastereomers. So the only 2 options left are constitutional isomers or identical. So which one do you think it is? Well, if we had constitutional isomers, we would have different connectivity of the atoms, but we have exactly the same connectivity of these atoms. So these are not constitutional isomers. In fact, they are identical. So partly they're identical because there are no stereocenters, but additionally, all the connectivity is the same. Now you might be thinking, wait, but there's a wedge and there's a dash. That's just representing that that carbon is tetrahedral. It's not really indicating anything else. So again, if we had constitutional isomers, they would have a completely different connectivity. So maybe the methanol group would be bonded to a different carbon, for example. Okay, so the other way to tell that these are identical is if you flip one of them over like a pancake, it ends up matching the other molecule perfectly. You might have to rotate it a little bit, but they're exactly the same. Okay, so the other two products that we have here is our solvent / nucleophile, and then the I- iodide ion. Now, again, notice that the oxygen in the product is positively charged, and that oxygen would prefer to be neutral. So now we're actually going to see something take that hydrogen from the oxygen so that it becomes neutral. So we have kind of an acid-base reaction or a proton transfer that's occurring. Okay, so we have two potential bases. Our solvent, methanol, could act as a base. It does have two lone pairs on that oxygen. Or iodide could act as a base. It has multiple lone pairs and a negative charge. So now, remember when we talked about basicity, what was most important? So one thing that was important was the stability of the products, but another thing with basicity is the atomic size. So if we compare oxygen to iodide, which one is smaller? Because that will be the better base. Oxygen. Oxygen is smaller. So that will be our better base. It will take that proton, and then the shared electrons are left on oxygen. Here I'll put in parentheses atomic size. Okay, so now we have our final products. And I'm just going to draw one of the products because, again, they're identical. And then we also now have a solvent molecule with two hydrogens bonded to oxygen. So, this will actually be positively charged. And then we have the iodide ion. Okay, so let's just summarize what happened here. So in the first step, the leaving group left. In the second step, we had nucleophilic attack. And then in the third step, we had proton transfer. Okay, so we had three different types of mechanisms going on here, but overall we had an SN1 reaction. Okay, so let's summarize nucleophilic strength here. So let's write out the periodic table, and we'll just write out part of the periodic table, so mostly the non-metals here. Okay, now let's consider a negatively charged nucleophile in a polar protic solvent. So an anionic nucleophile, and remember anions are negatively charged, and let's say it's in a polar protic solvent. Now, if we're considering atoms in the same row, remember we're considering electronegativity. And previously we said that if something is less electronegative, it's more likely to react because it's not holding on to its lone pairs as tightly, or its negative charge as tightly. So nucleophilic strength is going to increase going right to left. So let's say carbon had a negative charge. If we compared that to fluorine with a negative charge, remember fluorine is the most electronegative atom, So it wants to hold on to that negative charge. But carbon is more nucleophilic and it can attack something better because it's less electronegative. All right, now what about comparing atoms in the same column? So if we're going down a column, will the nucleophilic strength increase or decrease? Increase. So for instance, if we have iodide versus fluoride, fluoride can experience hydrogen bonding, so can oxygen and nitrogen. But as we go down those columns, those atoms cannot have hydrogen bonds with the solvent, so they're less solvated. But additionally, iodide's quite large, so it's difficult to solvate that as well. Okay, so let's consider an anionic nucleophile in a polar aprotic solvent. So this time we don't have hydrogen bonding, just dipole-dipole interactions. And remember, polar aprotic solvents don't solvate anything that well, or at least they're not going to have really strong hydrogen bonds. So if we're considering atoms in a row, will nucleophilic strength increase going left or going to the right? So again, we really just care about the electronegativity if we're comparing atoms in a row. So the trend will be the same. So the less electronegative something is, the more nucleophilic it is, at least going across a row. Now, if we're going down a column, does nucleophilic strength increase or decrease if we're in a polar aprotic solvent? It decreases. So it actually increases going up a column. And that's due to the fact that if you don't have those hydrogen bonds from a polar protic solvent, now we care about nucleophile strength in terms of atomic radius. So the smaller the atom, the more basic the nucleophile, and the better the base, the better the nucleophile. Oh, and let me actually write more nucleophilic at the top so it's not confusing. There we go. Okay, now what about neutral nucleophiles? So I'll make it easy. Neutral nucleophiles follow the same trends as polar protic solvents. So again, nucleophiles are stronger going towards the left if we're comparing things in a row. And nucleophilic strength increases going down a column. Okay, so this might be an easier way to remember nucleophilic strength. So if you're looking at a periodic table, you can kind of figure out, well, am I comparing across a row or am I comparing down a column? And nucleophilic strength always correlates with electronegativity. So the less electronegative an atom is in a row, the more nucleophilic. And then if you're going down a column, the only one that's different is the polar aprotic solvent. So typically nucleophile strength increases down a column unless you have a polar aprotic solvent, and then it increases going up a column in strength. Okay, so in the next video, we are going to discuss leaving groups in more detail, and then we're going to finish up our summary table where we summarized all of the different characteristics of SN1 and SN2 reactions. So I will see you then.